All right, so let's get started. Again, this is bathymetric amplitude processing in SonarWiz. Most of you are probably familiar with our side scan processing. Today we're going to be talking about swath bathymetry and how to process amplitude from swath sonars like multi-beam echo sounders, interferometers, and other swath generating systems. So today what I want to go over is how our swath or our bathymetric module works. It's an extension to SonarWiz. Then I'll show you kind of our quick workflow, how we import and process backscatter data from swath bathymetry systems, do a little brief comparison between the two, between a side scan and multi-beam amplitude. Then we'll talk about the statistical procedure that we use for normalizing multi-beam backscatter data. And then some of the tools we have for mosaicing and generating products from that data, from mosaics, generating grids, geotiffs, and that sort of thing. And then a couple of visualization options as well. So the SonarWiz Bathymetric module is an extension to SonarWiz. If you already have SonarWiz, it's a pretty small additional cost to add bathymetric processing to your existing SonarWiz license. The idea was to integrate swath bathymetry into our existing side scan, sub-bottom, and magnetometer projects so that you can continue to do all of your geophysical and scientific work in a single environment. It's designed to be easy to use, and we've tried to focus on our existing customers in the industry and marine sciences rather than duplicate features that are in hydrographic processing suites. We've tried to look at where our customers are coming from oil and gas, from search and recovery, from applications where side scan is already in use. So as part of that, we've needed to build the SonarWiz bathymetry to be flexible, adaptive, responsive to your needs. We are dealing with a lot of custom and hybrid systems, so we've tried to come up with a processing workflow that is easy to modify and easy to add support for new systems, and is flexible enough that it can deal with kind of old systems that are analog all the way through new stuff that hasn't been fully calibrated yet. We basically operate from the assumption that most of the systems we're dealing with are not calibrated, which has some impacts on what algorithms we can use and what our results will look like. So today we support multi-beam echo sounder formats from Kongsberg and Reason, primarily anything that's stored in a .all file or an S7K file, and a couple of other multi-beam specific file formats. We also support native reading of BathySwath, EdgeTech, Geoacoustic, and Klein interferometers, as well as a couple of others. And if those are the kind of the main vendors right now that we support, but we can also read anything that is recorded in HiPAC or in Quincy, including a lot of the binary extensions. For example, R2 Sonic doesn't have their own file format, so you would be recording it either in HiPAC, HSX, or in Quincy as XDF. And we can read those data either as native HiPAC files, or we can do a hybrid where we take the binary extension, this R2S extension for R2 Sonic, and marry it with the HSX and extract the backscatter from the R2S binary packets. Same thing with the Reason systems, and there's a few others that we support. We also do our own recording. We record into XTF format, and so we have our own extensions to XTF as well. And like I said, we try to, when we start supporting a new sonar, our preference is to try to support the vendor's format. We feel like this has the best, it's easiest for us to get good results from that rather than doing an export from the vendor format into a acquisition package format. Often for example, the HSX files have been downsampled or they've been processed in a way that we don't fully control. And so we can't produce the best quality backscatter from second and third party files. So what we try to do is go to the vendors and get the direct native file formats. And usually it's pretty easy to add these to SonarWiz. We have a lot of experience with that. We try to make the workflow as simple as possible, and it's very traditional. We start by importing native files, then calculate your bathymetry, clean the bathymetry, and then at the same time you're working with bathymetry, backscatter is being processed right alongside. So every single bathymetric sounding from the time you import it all the way through to creating mosaics is also having backscatter processed at the same time, or amplitude values. So the final step, the fourth one would be to create an EGN table, or empirical gain normalization, and I'll talk about what that is in a moment. And then you create a mosaic, which you can then export as a product. So basically each one of these green boxes is a place where you as the user will have to make some kind of decision or interaction with SonarWiz. So our main statistical tool for working with backscatter from swath systems is a technique called empirical gain normalization. And I want to spend a moment to describe exactly what that is. What you're looking at here is a small piece of the 2015 shallow water survey, and I've plotted the raw amplitude soundings as a map. You can see a little boat here, and there's some other targets on the seafloor, other wrecks, seagrass, there's light and dark areas. But when you plot all this stuff together and you show this like this, we can see that there's artifacts all over the data set. Each track line has its own set of artifacts. What we really want is the seafloor to show through. We want to see the stuff that's down there without the artifacts. So we try a statistical procedure. We take all of these overlapping files and we create the average of them. And you get something that looks like this. And what the average is doing is the things that we want to see are held steady. The boat's in the same position no matter which line goes over it. And so when we take the average, all the noise from the sonar system is reduced. It's not completely eliminated, but it's reduced. Things that stay the same are on the seafloor, and things that are changing are the artifacts on the boat and in the track lines. And those get eliminated. It doesn't work perfectly though, and we can continue to see the artifacts in the track line. So what EGN is designed to do is take this whole idea and flip it on its head. What if instead of trying to isolate the seafloor returns, we try to isolate the artifacts and eliminate the seafloor? In order to do that, we need to have a way of plotting the same amplitude data in a way that it holds the artifacts steady, but the natural variation in the seafloor goes away. So you take the exact same amplitude data and now you plot it like this. So in this plot, we're looking at exactly the same amplitude data, but here we imagine that the transducer is right up here at 0 and 0. And what we're looking at is amplitude that has been plotted with depth and a cross-track range. And we took every single amplitude in that same scene from here, and we plotted them now on this plot. So in this case, the artifacts are held steady relative to the transducer, but all the transient noise from the real seafloor actually gets averaged out. And what you're left with is an extremely accurate directivity index and beam pattern of the sonar system itself. This is the average amplitude for any depth and range from that sonar system. In this case, this is a Rezon 7125, and what we can see here is that the nadir region is actually brighter than the outer sections on average. And if you look closely, you can see individual beams coming out from the nadir where the amplitude, average amplitude is changing in value as you sweep into and out of the different beams. So we got all of this just from building this statistical table. Here's another example of the same thing. This is a EdgeTech 6205 interferometer. This actually has two channels. So you've got a port and a starboard channel. And here we can see one of the channels here has some kind of interference or damage in the transducer, and this EGN table is, or the gain table, has managed to pick up. You see these beams coming off of it like this. There's also changes with range. When they switch range, they're also changing gains, and the table's picking this up as well. So the more the sonar manufacturer can correct the data, the more we know about the actual broadcast and the better the corrections are, the smoother this grayscale table will look. Here's a third example. This is an EM2040, another dual head system, and this time I separated the zeros so that you could see that the beams actually cross underneath the vessel. In this case, the 2040 has sectors, and we can see that the individual sectors don't actually match grayscale-wise, but within a sector it's very nice. It's very uniform across that. But we can see from this gain table that we would need to correct this far outer sector with these inner ones. They're not. This one is lighter than the outside. So when we do a gain correction, we now have a map of what we need to fix it. So that's kind of that's how our statistical procedure works, but let's take a look at an actual data set. So this is a small demonstration data set that we use a lot because it has a really nice conventional backscatter. This is an EdgeTech 6205, and what we're looking at right here is the actual side scan. This is a high frequency side scan that was collected simultaneously with the swath bathymetry. And here shows, this shows a lot of what's really good about traditional side scan and also some of its problems. So if we look at a side scan waterfall here and we scroll down, here we're seeing a time series of pings. So it starts, the nadir starts in the center here. This is where the transducer is. The sound goes through the water column, it hits the seafloor, and then it starts to roll off across the seafloor. And just as if you were holding a flashlight down close to the ground, there are acoustic shadows behind things that stand up from the seafloor. Like here we have some debris on the seafloor, and you can see the shadows. The higher the object is off the seafloor, the more the acoustic shadow shows. We scroll down a little bit further, we start to see some sand beds here, sand waves. And then here we have some objects that are sticking proud from the seafloor, these barge structures. Notice how strong the shadow is in the back. There's no acoustic data at all here. This is absence of data. So what's really good about traditional side scan is that it has very narrow beams and a lot of resolution. You see a lot of contrast and texture in the data. What is troublesome about it, though, is we don't have any angle information. So we have to make a flat Earth assumption about where things are. And this leads to problems. So here I'm going to reveal there's multiple files here. I'm just going to slide one underneath. So we're going to peel the first one off. Oops, let's select this guy. Now pay attention to this edge right here of this structure. Notice that in the two overlapping lines, they don't match exactly. This is a function of some of the compromises we have to make using a flat Earth assumption and laying pixels down without having accurate bathymetric and angular information. Another problem that we have, if we zoom in over here, in addition to the fact that it doesn't necessarily line up, is that these shadows are averaged in with our backscatter data. So we can switch the view from cover up here to average, and now you see there's multiple images or shadows from each one of the track lines for where the data is. And over here you can see where we've got bright data that was imaged into this area and then shadow averaged together. So this area should probably be a uniform or homogeneous sand, but what we see is this big shadow that's cast across there, and that's because the line to the north was shining at such a high grazing angle that there was no data in here, and so you get this dark area. When you use swath bathymetry from a multi-beam echo sounder or from an interferometer, you can avoid these problems. So now we're going to take the exact same data and look at it from interferometers. So let's turn these off, and now we'll turn this guy on. So now we're looking at the raw bathymetric soundings, and we can see that the structures now line up much better. And we can also look at the raw backscatter. So let's draw, we go to bathymetry, draw backscatter. So like I said in the beginning, when SonarWiz imports data, we bring it in both the bathymetry and we color every bathymetric sample with the backscatter so that we can look at it. And you can use it from any of the views inside of SonarWiz. You can see this. So one of the areas, if we zoom in over here, where those shadows were, we can see that there's actually data in there. If we keep going in, you'll see that we're looking at the raw soundings. There's data in that shadow from the one track line that came along the bottom. Zoom out a little bit. And it's not only just in these views, we can also see them in our editors. So if we right-click here and open our swath editor, so it'll take a second to launch. Now we're looking at an across-track view, and a long-track view, and a top-down view of this data. We can open a 3D window here. As we step through the data now, here's the barge. So now we have backscatter amplitude plotted in space. And sometimes this is really useful when you're editing. If you're trying to decide whether a sounding in the water column is part of the structure that you're working with, or is it some sort of plant or a fish or something like that, it's being able to color the data by its amplitude is pretty handy. This also works in our area editors as well. We can select a polygon around here. This is a cool spot. And open that up. And now instead of showing just one track line, we'll see all the track lines together. So here on the left, we have the raw bathymetry with the backscatter. And then on the right, we have a temporary grid that was made from that data over here. So that's sort of a comparison of how side scan, traditional side scan, and amplitude data works. In this case, it was from an interferometer, but it's effectively the same from multi-beam echo sounders or any of the systems that we support in swath bathymetry. So when you first bring data into SonarWiz, let me walk through that. Unlike a side scan system, you'll need to have a vessel defined. So I've already done that for this data set. We'll show you here. For the Edge Tech, it's a two-channel system, a port and starboard side, and we've got the two channels here shown. It's got offsets to help correct for motion, and then patch or angle and roll is also corrected. Those two channels, when you bring them in, are required before you can bring in any data. Now for traditional side scan users, this is the side scan tab you would use when you bring data in. When you have the bathymetric module, you'll see these additional 4 items down here: bathymetry, tides, sound velocities, and external navigation. So in this case, we'll do a bathymetric file, and we'll pick one of these, and we'll bring it in. Actually, let's do all of them. It doesn't take that long. When the data first comes in, it's yellow here because it hasn't been merged. So we'll right-click here, merge it. SonarWiz has asks you questions about this. This is kind of outside the scope of today. We'll just do a simple error model. And you can filter. Now here's the same data that we were looking at without any corrections. This is raw, directly from the manufacturer. So when we look at the amplitude values here, they range from 66 to 97. In the EdgeTech system, that's not a calibrated decibel. That is just an intensity value with no units. But you can see this strong artifact in here. So how do we do the EGN work? So back to this again, we're going to go through a dialog here where we need to define the dimensions of this table, and then we're going to feed the data in. So the only settings in the backscatter processing for the bathymetry module are setting the dimensions of this table. The default values work for most shallow water systems. There's a horizontal range, a minimum horizontal range, and a maximum horizontal range, and that's just setting the x-axis here on this table. So here it shows 150 to 150. This graphic only goes from 100 to minus 100. Then you have depth from 0 to 100, or in this case 0 to 50. And then the table cell size. I used 10 centimeters here. You can use 1. These defaults work really well for most shallow water data sets. So here's how it works. So data is already gridded, or is already plotted in SonarWiz. It's already been merged. So we just go to the bathymetry tab and hit this process backscatter button. You check the lines that you want to correct. You go to this. Here we've got our settings from 150 to 150, 0 to 250 meters depth, and then a 1 meter cell range. Then we click Finish. And you can see when it's done how it will correct the artifacts here. So now the data, most of the cross-track artifacts have been removed from this data set, and we're looking at something that's it's a normalized backscatter, and the values range from about 80% to 119%. So what that is saying is for every pixel on this grid, we are falling somewhere on this plot. If, for example, if we were at 20 meters out and 20 meters down, this is the average value right where my cursor is, and that would be 100%. We compare the actual values that were measured here to those average values, and we make a percentage. So when something is above 100%, it means that target was stronger or darker. If it's lower than 100, it's a lighter or a softer target. So are there any questions so far about getting to this point? So, all right. All right, we are going to answer a couple questions here. So I'm not sure. So Emma, you had a question?
That's just the attendees.
I can hear you if you're talking. Let's see. All right, how about, I'm going to take everybody for a moment. How about Emmanuel, did you have a question? No? Okay. Any other questions? How about Michael? If you do have a question, just go ahead and chat or type it into the chat box here. I'm going to keep going then. So once you've generated these points, at this point we've made no decision about the resolution of the data set. If you zoom in, you actually see the raw soundings. Now for this EdgeTech data, it's been binned, and the binning is at about 20 centimeters or so. So one of the things, the first thing we're going to want to do here is create some kind of grid, or a mosaic of these data. And that brings us to the second basic process here. So we click on the Grids tab in the Project Explorer, right-click and say Add or Import, or excuse me, Create New Grid. And this dialog pops up. The upper section here defines the window that you're looking at, or you can click this button here and just drag a small window that will adjust these bounds, or you can just type them in yourself. You set the cell size, and then you give a root name. It's like we'll use blend. Then you go through these windows from left to right. The first thing you want to say is, what is our primary grid going to be, an amplitude or a depth grid? So we'll make an amplitude grid. Then you select the algorithm that we're going to apply for creating the mosaic. We provide currently 6 different algorithms. The mean, which is a trimmed mean, and it also includes footprint size when it's being created. So it's not a bin per se, but if there's uncertainty in those soundings, it will spread them out to account for how large the beam footprint is. There is a median grid, which just takes the medium of every overlapping cell. The blend, I'll explain in a moment. We have nearest range, inverse distance weighting, and then preferred angle weighted. In addition to that, this primary grid that you can create, you can also export another grid that has statistics such as the count, the minimum value, the maximum value, a simple mean, and standard deviations. So some of these, for example, the mean, the median are pretty obvious. Most software have that, but these last couple are worth explaining in a little more detail. So let me go back to my slides for a moment. So when you have an, So when you have 2 overlapping swaths, so here we've got swath A is here in blue, and then swath B is in green. Now let's assume that these are amplitude values and you have the overlapping swath. And you want to make a grid from these overlapping swaths, which is this black line here shown at the bottom. If you use the algorithm of a mean, what it does is it's fine when it's only swath A, the resulting grid will look just like swath A. If it's only swath B, it's going to look like swath B. But where the 2 overlap, it averages the 2 values together and you get something along the lines of this black line. And what that winds up doing is it introduces 2 steps into the data. One when the blue line steps down to the black area, and then another one when it steps from the average down to the green line. And what that will introduce is 2 edge artifacts for every single one of your overlapping lines on each. So wherever there's an overlap between 2 data sets, if you use the mean, you wind up with 2 edge artifacts. And you'll see this stair step down between them. And it kind of destroys your mosaic. So you might think, well, let's use the median. Well, the median chooses between the overlapping area based on how many soundings are in populating each bin. So if you have a bunch of soundings in swath A and very few soundings in swath B, then it will pop up and use swath A, or something, maybe some noise in between. So you wind up with a real jaggy, an area zone of edge artifacts that kind of pop up and down between the 2 data sets depending on how many samples fell into each bin. Another option is to split the difference. That's what nearest range does. So where you have overlap, the nearest range will divide the overlap in half, and it assigns all of the data from the resulting grid up to the midpoint. Will go from swath A, and then once you've crossed the midpoint, everything from swath B is plotted, and there's no overlap at all. You'll generate 1 edge artifact where you step down from swath A to swath B, but over where when you're off those things, there's no overlap at all, and importantly, there's no blending of the values. This is really useful if you're trying to do target detection. For example, you're looking for an unexploded ordnance on the seafloor, or even seagrass, things that are proud of the seafloor. You don't want to blend and average or smooth out two overlapping lines. Because remember, we're just showing 2 lines here, but it could be 10 lines or 5 or 6 lines overlapping each other, all from different angles. And has a tendency to kind of blur this overlapping area. The nearest range will always it will always fill the pixels with the data that's closest to nadir. So wherever that swath happened to fall, it only displays one swath track line at a time. The final one that's worth talking about is blend. And the way this works is once you start an overlap, it gradually uses this cosine weighted curve to gradually change the weighting from swath A to swath B. And what you wind up with is a resulting grid that kind of smoothly transitions from one to the other with no strong edge artifact and no stare. This is actually the best algorithm to use if you're doing habitat mapping and you want to try to minimize the differences between overlapping lines. What it does is it effectively, and very effectively, eliminates the edges between all the data sets, or between every track line. It doesn't eliminate nadir, but it does eliminate the outside artifacts. The final one is what we call preferred angle weighting. And what this does is it weights, you as the user will select a preferred azimuth that you want to illuminate objects from a particular direction. And SonarWiz will weight beams that are in that particular direction much higher than beams that are from other directions. Finally, the sector size here, it will only accept data that falls within the sector. So the default is you would pick a beam azimuth and it accepts data from all 360 degrees on either side of that, or 180 degrees plus or minus from this beam azimuth, and it plots them all together. But the weighting is for your preferred azimuth. So you'll always get data all throughout the data set, but it is preferred from the illumination angle that you selected. If you only want to see data from, say, 90 degrees, like I've shown here, you can make the sector size smaller, and it will only plot data that is illuminated from this direction. And it goes through all the track lines, no matter which direction the vessel was pointed when you collected the data, and it will do this for you. So you don't have to manually select what lines go into each binning process. So that's what these algorithms do. So the mean is just a simple mean. Here's the median. Blend uses that cosine weighted curve to blend the edges. Then we have this nearest range and inverse distance weighted. I didn't explain this one, but that's a simple interpolation algorithm that fills gaps. And then we have this preferred angle weighted. So let's try blend here with a 25 centimeter cell size. And then we'll add that. This doesn't take very long. Now, SonarWiz is displaying the actual amplitude soundings over the top of the grid, so we can turn off, we can change the way we display the bathy. So we go to drawing mode, bathymetry, and change it to navigation plot mode. And now we're seeing the results of the grid showing through. So this is blended. You can see between these two track lines, there's very little artifact, almost none. It's blended that together. So here's the blend. We can also make let's try making a nearest range one. Let's see if that changes things. So now we're looking at nearest, where it's going to switch immediately down the center. It switches from this southern track line to the northern one. It does the same thing right down the center here. There isn't a huge difference here, but you'll notice the nearest does a better job of picking out edges. And when you want to see shadows, if there's shadows in the data set, or when you want to only present data from a particular target. The nearest does a better job. I suppose the only area here that's really interesting is the spot where those targets were at. And you can see it's a little bit better with nearest. And when I turn the blend algorithm on, it kind of gets a little smeared out. And that's because we've averaged illumination from multiple directions. Once you've got a grid, you can export those grids. And we support virtually everything that Global Mapper supports. So we have like 15 or 20 different export formats for grids. We can also save the data as a geotiff. Let's add a little more contrast to this data set here. Maybe by changing the color palette a little bit, we can add a little more black into the data. It looks a little darker there. So we can save this as a geotiff. We'll call this one the swath amplitude. Click Save. Now I'm going to quickly make a bathymetry grid here as well. It's the same basic process. We can do cube. And we're just going to skip the statistical stuff. Now we have a bathymetry grid. I think 8 here. What I'm going to do with this is pull all of our data. Oh, let's make one more geotiff. Just to compare the difference between an amplitude grid and the side scan grid. So we'll switch here to, we'll switch the side scan mode to cover up, because I think this has the best resolution. And now we'll export that as all right, there we go. Now export as a geoimage with side scan. Call this one side scan. That can be higher resolution. Oops. All right, so now I'm going to right-click this and open our grid in the 3D viewer. Now here's our bathymetry grid, and this is, we can expand it or shrink it. Control the color here. Oops. Yeah, that looks better. Now what I'm going to do is pull in that georeferenced image here. So the first one, that's the one we just made. Here's the side scan and the swath amplitude. So when we pull that swath amplitude data in, it matches exactly over the top of the bathymetry. And we can just, oops, drape it right on top. There were a few holes in here. We could have interpolated those a little better. So now you can kind of get a sense of what the resolution of amplitude backscatter is. This was 1/4 meter resolution. If you want to do the same thing, I think I can do this. Pull the side scan in to get a sense of the difference between amplitude and side scan data. Let's see if I can switch. Now here I am. So part of what we're seeing here is the higher resolution of the higher frequency in the side scan. We're also seeing shadows, which adds texture to the image and makes it easier to find targets, especially over here. But those are sort of the trade-offs between traditional side scan. Now the side scan in this case comes from exactly the same fish as the swath bathymetry does. This 6205 interferometer has two bathymetric channels, and it has a side scan channel for port and starboard side. So you can kind of get a sense of the difference between side scan and swath bathy here. The downside, depending on what your application is you also get the shadows. So we've got the shadows on the sides of this structure. It helps you find those targets, but if you're doing habitat mapping, for example, this would be an area that you would incorrectly classify because it's not showing any data. There's no sand down there. So that's a 6205 system. So it gets a little bit more complicated with some of the multi-beams that have optional backscatter packets. So let me show you one of those as well. So I'll close this down. I'm going to open up a project here that has swath bathymetry from a 7125 Reson system. So with Reson data, we have a tool here that lets you inspect the packets that are inside this S7K file. So if we go to this extract packet information, and we'll switch over to the S7Ks. So I'm going to just sniff one of these S7K files and see what's inside of it. We make a little CSV file that you can open in Excel. And this is over here on the left is the packet record number, and then the type of packet it is, and then the number of records that we saw. So for the S7K file, there's actually multiple options for backscatter. In this case, you sometimes see a 706 packet, which is just the beam average data. That's not present in this data set. But we have a side scan. This is a pseudo side scan that is collected exactly the same way a traditional side scan would be. It's just a time series of amplitudes from the broadcast to the ping to the end of the range. It has no angle information in it. And then we also have the 7028 packet, which has snippet data in it. Now snippet data is individual samples or amplitude samples within a single beam. And because we know what beam we're dealing with, we can map that data onto the seafloor pretty accurately. The resolution is very high compared to beam average data. So when you import these data in SonarWiz, you have to make a choice about which of those side scan packets you want to use. So we go to post-processing, import bathymetry, and we'll just pick the first file here. And we have this option of file type specific options. When we support a file format that has optional choices like this, we add information to this tab here. And you can see with HiPack, you can pick the devices, you can say where you want the backscatter to come from, whether it's going to come from the side scan packet or the beam average packet, etc. For the S7K file, here we can see these packet numbers again. So where's the bathymetry going to come from? In this case, it's the 7027, the raw detection data. We have 4 options for backscatter source. You can get it from the side scan data, the snippet data, or the beam average data. We even support the old snippet data that the 7111 uses, the 7008. And then you have 2 choices for how you want to plot the backscatter. The first one, and the one I use for most shallow water data sets, is just take all the snippet data here and use statistics to try to reduce it to our own beam averaged value. So we take the snippet data and we calculate a better beam average value than what you get from Reason, and just use one value for each beam. That's this option here. If instead you want the full resolution snippet data, you can click this button, and what we do is we take the beam data and lay it out, and then we interpolate the snippet data onto that surface. So effectively every single snippet sample gets an X, Y, and Z value and then can be plotted in SonarWiz. Just for speed's sake, we'll do this. And this particular data set is so shallow that the difference between the interpolated snippet data and the beam averaged is not much. There's only, the beam average data is typically 5 to 7 centimeters across, and this becomes 1 centimeter across, and it's really, it just doesn't do much for the imagery. The rest of these are for selecting where the navigation is going to come from. So we'll bring that in. Again, we have to merge it. Let's make sure it's selected. And then pick the correct vessel. And now we're looking at, this is the beam, it's our beam average snippet data, and it's plotted directly from the Reason system. So these are the raw data from Reason. We turn the rest of these guys on. You can see this is the raw data, so you can see the edges between the individual samples here. And we're going to do the same. We can look at the bathymetry as well. So you can switch back and forth between these two. And we'll just run EGN on this, just like we did on the dual channel system. So go to bathymetry, process, we select the S7K files here. I've actually got some EdgeTech data in here as well. Just use the defaults. And this will take a minute or two for it to process. So it sounds pretty simple, just creating one of these tables and working with it. There isn't a whole lot of user interaction, but that was by design. We don't want the user to have to do a whole lot of pattern matching between individual lines where you need to change gain settings to make things match. What we're trying to do is handle all of this statistically for you. And it works extremely well regardless of what kind of sonar system that we're working with. I have data here in this project. As soon as this finishes, I'll show you what the entire data set. There's 101 track lines here, and although it's not perfect match line to line, it does an extremely good job of the entire regional data set with no user interaction at all. And you've preserved all of the resolution that you brought from the original data. That's a really important point about EGN. There's no smearing of the data sets to make it look nice. Every single sample that you collected is preserved. You make a choice about the resolution that you want to export when you make the grid, not when you're doing the backscatter processing. And that means that you, with a single set of processing, you can zoom into a target and work with it at full resolution, or you can back out to look at a regional map and make that at 5 meters or 2 meters, whatever you choose. So this is almost done here. The downside, I think, to statistical processing is it takes about between 30 seconds to a minute for each track line that it's working with. However, you don't have to sit and babysit it. So now those data match very well. Go here to backscatter. Again, this is a normalized value, so it's ranging from, it's maybe a little too much, say 50% to 150. There you go. We can zoom into I have some targets picked out here. So here is a target. We can open this up in our area editor. The 7125 for this data set did a really nice job of picking up the seafloor targets. It's like a, looks like there's some noise down here. Try to delete that. Oh, when I brought in that new data set, I didn't correct for tides to see how this one's floating up above. You can see this target looks really well. I haven't cleaned anything, and it looks really nice. And when you zoom out a little bit so that those points converge, you can start to see the backscatter pattern. There's a port and starboard side of this target actually has different sediment grain sizes. Here's this is a grid made from that same data. It's interesting to compare this with the side scan files over the same area. I think this one does it. And we can look at this. Here's that same target in the side scan. Maybe not the best side. We'll go here to, here it is. So you can really see it well in the side scan data where those targets are sticking out. There's also a boat in this data set down here. And that looks really nice in this data as well. So that's basically our options for this. You can see how this all blends together pretty nicely. We didn't have to do anything, and you can there's seagrass down here or some sort of gravel. When you zoom in down into the center of the channel, there was some pockets of, looked like some patchiness down on the seafloor. All of that's real. If you go down and do coring through this, it's very sensitive to these kinds of changes. I quickly made a grid before we started the seminar that just shows the whole data set together and kind of what you can expect to see out of a larger scale survey. Let me zoom out. Oops. Yeah, too dark here. And turn off the side scan line. So here's the entire regional area after it's been gridded, and then I blended the lines together. And there's a little bit of a nadir artifact here. But what I really want to emphasize is we can, because we don't need a specific model of the sonar, we can do this kind of processing on various different types of sonar in the same project, and their grayscales will match pretty closely to each other. And it does a really nice job. You can pick up a lot of detail in there. So that's what I wanted to cover today. If there's any questions, now would be a good time to ask them. Is there anything? If not, please let me put our website up. Feel free to contact us at www.chesapeake.com and chesapeaketech.com. sonarwiz.com. Here it is. And thank you for watching.